So welcome everyone. My name is Natan Silnitsky and I'm a backend infrastructure developer at Wix.com. And this talk is about the key patterns that I have implemented or have witnessed implementations of at Wix that have enabled us to create a robust, event-driven, distributed microservices environment that can easily handle increasing scale and traffic and storage needs. But first, a few words about Wix. Wix is a website building platform that allows you to manage your online presence and manage your business online. And we have more than 200 million registered users from 190 countries. About 5% of all internet websites run on Wix. Our microservices environment comprises 2,000 individual services. And we have more than 1.5 billion Kafka messages produced per day, which means we have quite a lot of event-driven use cases for our microservices. And the agenda today is going to be about how we can move away from monolithic design and towards microservices environment in the event-driven style. So we have a consumer project that's about a pattern about how we can create services with the materialized views that help us with optimizing queries and also moving away from the monolith to disjoint microservices. And then the second pattern is event-driven from end to end. So here we see how we can combine Apache Kafka and WebSockets in order to have full event-driven flow from the browser all the way for all the cooperating microservices. Then we'll touch on the zero-latency key-value store pattern, where we can have storage that we can access in memory with zero latency on top of Kafka and Kafka events. And then we'll see how we can actually perform event processing in our microservices, but with the guarantee of exactly once processing. So we can make sure that for high-risk operations, there is no data corruption. So we started off in the industry with our monolith that did everything. And then we saw there are quite a lot of advantages to actually moving from monolith to a distributed microservices system. That means that services can be deployed separately, can scale up separately, and have different requirements and needs. But what about the database? So if we have still in the monolithic approach, one big database to support everything, that means that we have mutable state that is shared by all of these services, which is not good, and high contention for possible that all these services may need to access the same parts and increase latency and reduce performance. And also no flexibility of choice. We'll only probably use one relational kind of database, and that's it. And that's really not optimized for all kinds of needs for our microservices. So instead of that, usually with a microservice, you'll have the data encapsulated behind the service. Each microservice will have its own kind of database, offers optimal flexibility. Maybe you want NoSQL, graph database, whatever suits your domain logic. And also schema can evolve easily without needing to worry about mutable shared state and other conflicts with other services. Now let's talk about microservices communication. So if you take, for example, an e-commerce services, we can see here we have the checkout service, and it requires all kinds of collaboration from other services here, like payment service, user service, and inventory service. Now, we can go with the classic request reply model and have HTTP or RPC requests be done from checkout service to these services, but that's a bit problematic. First of all, we encapsulated the database, meaning that for each of these requests, the service will need to go to the database, fetch the information, and bring back the result. So we're doing these requests one by one. We don't do any joins here between these tables because each is in its own separate service. So this is quite a slow operation. And also there could be network issues or something that it makes the service go down or maybe a bit unreliable, meaning that now the checker service that needed to have this information online now because of some request from the browser, it doesn't have it. So it will need to fail the request back. So it's really unreliable model. Now, if we introduce a message broker between our microservices, then we can have a bigger degree of reliability. Messages are produced to a cluster of brokers. So there are a lot of cooperating brokers with a lot of redundancy between them. All of the data is replicated between the brokers. So we have a much higher degree of reliability for these message broker clusters. And also, because we're producing messages and consuming messages, we're actually completely changed the flow model. So flow control is moved from the sender here, which doesn't really know what's going on other than it produced the order created event, to the receiver. So the control here is going to the consumer side. And this means a much more robust approach, because even if the producer is currently down, we still have all the events that it produced up until now to consume. And this solution means that the consumer can consume it in its own pace and really gain the full advantage of not needing to have an online server to call. Specifically, this talk focuses on a message broker of type Apache Kafka, which you can define as a distributed log broker, where each topic that messages are produced to is divided into partitions. And these partitions have linear scaling, meaning that if you need to have bigger traffic, bigger throughput, all you have to do is add more partitions, and then you can handle more traffic. Of course, you also need to have more instances for your microservices to have this increased processing rate. And these partitions are basically commit log files where events or messages are written at the end of the file, which means it's much more faster than other kinds of data storage models. And you can see here that message producer produces the message at the end of the partition, and data can remain here actually indefinitely. It's not like with traditional message queues, where once the consumer consumes the message, it is actually removed from the topic. The messages stay basically forever. You can set it up, although the default is to serve it for 1 week. And then consumers are just passed through sequentially each partition, and once they finish processing a message, they will commit it, meaning that if there's some restart or the service starts up again for some reason, it will start off on the assigned partition from the first message that is not committed yet. So this way we have the efficiency and throughput of processing from an append-only file in a very fast manner. It can also be a lot of times in memory, and still have the flexibility of knowing which index to start consuming from. And this data model is immutable because we only append, we don't change data in place, meaning it's much more resilient and much easier to debug as well. And we can also guarantee that processing will eventually succeed, because if there is some failure with processing the message, we know that because of the sequential property, we can eventually retry and retry until we succeed processing the current message and only then commit it. So if we look at our ecom example and try to switch it to the event-driven model from the earlier request-reply model I showed you, then here we'll have communication between the checkout service and the other services actually done via the intermediary, the Kafka broker. And each topic will have each service will be in charge of its own topic. So the payment services has the order topic that can it can fetch orders from and actually perform payment. And the user service is in charge of the user's topic, etc., etc. So we can think about these topics as actual storage of that the checkout service can easily access and consume messages from, or in the case of orders topic, produce messages to. And that means that we have much greater decoupling, much more flexibility. You can also cache some of the information in your own service, and you are completely decoupled from the need to just query each service separately and have much better performance. Okay, great. So like I said, we're going to talk about the 4 specific patterns. Now we're actually going to drill down on what it means to do event-driven style of programming for microservices. And these are based actually on a blog post I wrote, and very popular. It helps a lot of developers and architects. And all these patterns are used quite widely at Wix microservices. So the first pattern is consume and project. So imagine that you have a service that it has very high throughput. In our case, we have the metasite service that stores all of the metadata that is part of a Wix site, including which applications are installed on the site, what's the site version, who's the site owner, all kinds of relevant information. And we have all kinds of other microservices at Wix, including verticals like stores or booking, scheduling, and restaurants that actually require to get information of this monolithic service, the metasite service. And it had a traditional database with a large metasite object serialized for the database schema, and a lot of read and write requests. Actually, it got up to 1 million requests per minute. So quite a heavy load and contention on the database. So the metasite team decided they thought about how to reduce this contention and get better reliability and performance and not risk database failure. And they did this by first taking a part of the data, only the site installed applications, and seeing how they can actually remove these requests from a site service. How did they do that? So first, they actually produced to Kafka each and every change that is done to the database. So a site is updated, its metadata is updated, and they produce the metasite object to the Kafka broker with all the changes. Then they created a completely new service called a reverse lookup writer that it consumes these messages, events on updates to metasites, but it only filtered to get updates on which apps are installed on the site. So it acted as a filter or a projection and only consumed the site application installed context and put it in a brand new database table. And the third part here is that they had another service called a reverse lookup reader that actually was in charge of reading from the database. And now we had queries that are optimized just to get information on apps installed, and it can easily be fetched from the database. So what are the advantages of this kind of migration and new architecture? So first, we produce messages instead of serving them. So that means massive load reduction on the original database table with the entire metasite object. Second, because we projected the information, then we can have highly optimized queries like materialized views to only the information that is highly needed, like which apps are installed on the site for our different various verticals to query. And also importantly here, there is this read-write split between a writer service and a reader service. So with this approach, it means that it was really easy to only scale the reader databases. So we can have replicated instances of the data for read-only state. And this means that we can have a lot of replicas in only one original master database to get writes into, which means it's much more resilient. We know that these read-only databases can't be corrupted and are easily scalable because you just need to add more as you gain more throughput and popularity for these kinds of requests. So it means that by adding more services and utilizing the power of Kafka, we could really switch the metasite service from its monolithic approach to a more distributed microservices approach and gain much better performance and reliability. Great, so the second pattern is event-driven from end to end. So we're talking about how we can have events be part of browser to service interaction, which may sound a bit weird. For instance, let's look at the following use case. We have a long-running asynchronous business process. So imagine that you want to have a service that imports contacts from various platforms like Gmail and stuff like that over into the Wix configuration system, CRM system that manages the Wix site owners, contacts, and visitors. And maybe they want to send some email to notify something. They want to keep all the contacts that they have and put it on the Wix platform. Cool. So we want to start thinking about how to actually create this architecture. So we have a contacts job service, and all its job is to actually create these import jobs. So it produces a job, maybe separate jobs for importing from Gmail or from Outlook or from other stuff, or maybe other concerns it has. Maybe they need to split up big lists of contacts into smaller jobs. And then we have the contacts importer service that will consume these requests and actually do the import actions themselves. Now, if you see, we're producing a request to Kafka, but we cannot actually get any request back yet because the operation here is asynchronous. We're actually sending an event. So how will the browser know when the import process is finished or it's 50% done? So for that, we're going to actually have the browser subscribe to get WebSocket notifications from Wix's WebSocket service. And then when it requests to import CSVs, for instance, from the front-end service, then it will also provide a channel ID, a WebSocket channel ID, where results can be brought back to the browser. And this channel ID will go to the import job request coming into Kafka, including the channel ID. And then when the consumer is finished with processing some job, it can actually update the WebSocket service that job 1 out of 10 is completed, and this notification can be brought back to the browser. And the browser has no idea that multiple services are part of the processing of import business logic. It's completely decoupled, but for the user, it's completely seamless. Now, another cool thing that you can do with Kafka is that you can actually take these job import requests and replicate them across different data centers and have the actual operation of import be done on a different data center. Maybe that's good because we know that the best Outlook server for getting good performance when doing imports from Outlook is in an Asian data center. So we get the original request on a European data center, but then all of the Outlook requests will only be processed in Asia. So it's a completely distributed global operation, event-driven from end to end, from the browser all the way to the last involved microservices and back. So you can see here that no polling is required. We don't need to keep some status in a database and have browser keep asking what's going on, is it finished yet, and keep updating database and making sure that we have locking or optimistic locking, stuff like that. We don't need to do any of that because we have complete event-driven flow, no polling, and we can just bring back notifications when jobs are done. And it's scalable because it's really easy to spin up more import job workers as required, like we talked about earlier. And the replication property of Kafka topics means that it's really easy to have cross-DC requests and cross-DC processing. Great. So the third pattern for this talk is the zero-latency key value store. So this talks about how to have information that you want to have readily available and not keep up the user request waiting from the browser. So for that, we have another feature of Apache Kafka brokers that's called compact logs or compact topics, where we have, for each record, we have a key and a value, but the Kafka will not delete messages that are stored after 1 week, but instead it will remove messages where there is a stale value for the same key. So in this slide, we can see that for key 1, there is already an updated value of v2. So that means that key 1 and v1 can actually be removed. So at Wix, we created a data structure called key value store reader that has an in-memory map where on the service startup, we'll read sequentially all the partitions from the compacted topic and create an in-memory representation of this information. So we see that for key 1, v1 is changed the value to v2 as the processing is progressed. Then we add key 2, v1, and key 3, and so on. And once the startup phase finishes, we have a complete representation of the key value store in memory. So of course, it's not good for data that can basically, data sets that can basically infinitely big. It's more for data sets that you know will be contained in size. For instance, we have the business manager service that stores information on the countries, which countries currently Wix is operating in, for instance. So we have the countries topic in Kafka, and it can load that information. And we can also have, for instance, the booking service that is in charge of helping site visitors book lessons like yoga lessons, stuff like that, from Wix site owners. And here it's very important to know what's the current time zone for each country. So we have the time zones topic, and we have a reader for bookings to actually keep all of this time zone data in memory. So now let's look at how we update this memory. So for that, we have the key value store writer data structure, where the business manager is updated that a new country has now Wix operating in it, for instance, South Sudan. So we have a simple producer here, just produces a new key value for South Sudan to the country's topic. That's all, nothing special here. But then we can have the business manager service itself or other services have a key value store reader for country's topic themselves. And it has a built-in consumer in order to get updates online. So once business manager updated the country's topic, and it means that bookings can have immediate update also for its in-memory representation. And now bookings notes that it needs to add for its time zones storage the time zone for South Sudan. So it looks it up in some HTTP request and then brings it back, updates the time zones topic via the producer, and voila, we have the South Sudan key value for the time zones key value store. And then we want to update some data, some time zone for Albania, for instance. So we have key value store writer, update that, and it's updated automatically because we have the consumer listening for updates. And then other services can also have their own stores, etc. And what's nice here is that all the different services in the ecosystem are kept up to date all the time because they have this consumers. And so we not only have zero latency for the bulk of the key value store that is read at the beginning, it's also kept updated throughout the lifetime of the service. Okay, so what does this pattern give us? So we have zero latency key value storage for the dynamic configuration, like time zones, like available countries. Notice that compact topics is still a topic. Other services can consume it regularly and get updates, like we saw. Now, like I mentioned, it's very important that you won't use it for general purpose data sets that are dependent on, I don't know, scale of traffic and stuff like that, because then you will not fit into memory. For that, a better approach will be to have a disk-based database that you use and an in-memory cache on top of that, it could be compact topic, or maybe when scale grows, it could be regular topic that gets updates from the database, and you just decide how much of the topic to keep in memory in the beginning, so it's more scalable. Great. So the last pattern for this talk is having events done in transactions, meaning that no matter how many times Kafka may accidentally process the same message, we don't alter the state of the side effect of the events that causes the side effect. It keeps being idempotent. And let's see how it can be done quite automatically by using new features that Apache Kafka provides. So we have here a classic e-commerce flow where we have payment service, and we're doing this in event-driven fashion. It announces to the world that a payment was completed. It produces an event to Kafka. Then we have the checkout service that is consuming this from these payment topics, and it also produces an event that an order is completed along with all of the items that are part of this order. And then we have downstream services that consume these order completed events and perform side effects. Like delivery, they want to make sure that it's packaged and delivered all of the items on the order. Inventory needs to be reduced in order for correct operation, of course, and an invoice needs to be sent along with all of the items in it. Great. So, of course, we can have multiple situations here where, because of some restart or failure, we'll have multiple times where we consume messages, and basically we can end up in a situation where we handle the same event more than once. But that's not good, because then we may deliver the product more than once. The inventory may be incorrectly decremented twice or more, and stuff like that. So the traditional approach to solve this is to have a database that keeps track of which completed orders have been successfully processed, and these services will need to mark when they finish processing it, and have some maybe optimistic locking and stuff like that, or regular locking for your database queries. But that's quite a lot of boilerplate that could be avoided. So how we can avoid it? So we can switch each part of this flow into being more idempotent. So for instance, the producer at the beginning of this flow can be changed to be to change to an idempotent producer. And that means that it will make sure that the message is only produced onto Kafka. It does that by attaching an offset to the message. So here you can see how it will make sure that it won't produce the message more than once, because it says, okay, I produce message 0 and put it in offset 0. I produce message 1, put it in offset 1. And then the producer says, okay, there was some restart, it didn't get an acknowledgement, and it says, I'm producing message 1 again. But then Kafka will say, wait, I already have message 1, and it completely ignores it. Now, about the rest of the flow here, it's a little bit more complicated than the idempotent producer at the beginning. Actually, Kafka creates a transaction between the consumer producer here, or processor, and the downstream consumer. And this has quite a lot of details into it, which I won't get into because we are short in time. But I'll give you more information at the end of this talk, so you can query it yourself if you're interested in how exactly these transactions are actually implemented. I will say that the consumer side here will only view messages after they are successfully consumed and produced once by the service in the middle. So there is a bit more boilerplate to setting up these Kafka transactions, and you will need to perform tuning because the more messages you put in a transaction, the less the overhead of performing this transaction will matter, but you will incur latency because the downstream consumers at the end will need to wait for all the messages to be produced for this transaction, and only then, when the transaction is completed successfully, will they be able to consume it. So there's a trade-off here. And database updates or third-party calls are not covered. They are not part of what Kafka has control over in order to make sure they are idempotent. But you can deduplicate writes to database by using the Kafka record offset itself as a version to make sure that you don't update for the same version twice and decrement the inventory twice mistakenly. And I wouldn't recommend turning on these transactions by default. I would only use them in critical flows where exactly once processing is mandatory, like with payments processing, for instance, but not for any old event processing that you perform in any microservice because of this overhead and more complexity. And if you want to have more information, I actually gave a talk on the matter of exactly what's delivered with Kafka. And I put the link here in SlideShare. So don't worry, you'll have the link to this talk. And I want to summarize now. So Wix developers have employed these event-driven patterns to make the microservices more decoupled, resilient, and scalable. And you can also, a lot of the patterns here have partial implementation done by our Apache Kafka SDK client that we have for the JVM called Greyhound. So it's open source and you can check it out as well. It has a lot of cool features, enable parallel processing and consumption, resilient retries, and batch consumer, and a lot more. So you can check it out on this link. So thank you very much. Really enjoyed giving you this presentation. And here are more resources where you can find out about the patterns that I gave in this talk. I have 2 blog posts on this matter. And also there's a great blog series about moving to event-driven style development of your microservices by Ben Stopford from Confluent, the company behind Kafka. The disadvantages of having shared database by Chris Richardson, also a great resource, and the talk I gave on exactly once delivery as well that you can check out. And all the links here I put in SlideShare, so you can just find me on SlideShare and find the slides there. You can also follow me on Medium and Twitter for everything that we are up to in data streams team at Wix around event-driven architecture, Apache Kafka, and also software engineering best practices in general. And you can also check out my website at natansil.com. And there you'll find links to all the previous talks I gave at conferences and more material. So thanks again. I'm done. Okay.